So fun fact is, actually, I was the organizer for Untitled for the longest time. I never spoke at my own conference, but this year, Jeff is running it, so I get to relax and actually get to share my stories. And my name is Macy Kuang, and I'm a software developer. And years ago, I think about 5 years ago, I really got into hardware. And I want to really understand how can I transition myself from a software developer to someone who can understand hardware. And yes, so I will share you my stories about my transition and tell you how I shipped my prototype of IoT products into consumers and turned it into actually profitable commercial products. So a little bit about myself, I'm a game developer professionally. I've been making video games for over 10 years. I worked for many different game studios, and about 6 years ago, I became independent. I have many customers. I still make video games. Like, for example, for Peppa Pigs, if you have a kid in your family, Peppa Pig is a very popular British pig, and I released the iPad game for them. And also, I work with a lot of hardware, software integration installations for different exhibitions. So I had customers such as Canadian Tire, Air Miles, and many, many more. And of course, have a lot of affiliations. I feel as long as you work in the industry long enough, you're getting different affiliations. So I'm also affiliated with Google and Intel in categories such as IoT, gaming, and also wearable, which is interesting. And I think we all struggling in this industry, like why it is so hard to ship new wearable products. I really want to figure out why hardware industry is so hard to breaking into. And there are challenges. Of course, like we all did this. If you ever got an Arduino board or Raspberry Pi or whatever board out there, the first thing they tell you to do, let's just light up a light. But I don't get it. Like, I feel there's a glass wall between me and the real robotics, right? Yeah, like light up light. It's like I can get that done within 5 minutes. And how do I make this killer robot? Maybe the robot's friendly, but it's like a dog. A robot dog can balance itself, and it can move forward, it can carry things. Like, how do I transition this knowledge from turn things on and off to something like this? It's actually functional, actually has a purpose, and it actually looks cool, right? How do I do that? And I did a lot of research. I decided I need to actually go back to school for it because the knowledge for hardware just not as accessible as software. There's no like GitHub. Well, there may be, but I still don't understand how to compile the code. And if I run into a problem in hardware, I really cannot really get help online because all the wires are messed up. I can't really take a picture to somebody, show them my wire. They cannot really figure it out remotely. It's not a problem, can be simply solved offline. And then I decided I want to learn this, and eventually I understood what are those things means. And yes, they still look a little bit foreign to me, but at least I know why and how to use them and when to use them. And surprisingly, I learned other things I never thought I need to learn. First, I learned how to draw for production. So we are not just having pictures, some sketches. I learned SolidWorks, which is a commercialized version of 3D modeling tools for commercial use. If anyone who want to make a physical hardware, especially home appliances, their devices has to be like drawn in like a professional way, and it has to be machinable. It has to be able to source the components from different parts of the board, and also I learned about different motors. I understood how different motion works. If I want things move a certain way, what should I do? The most surprising thing I never thought I would really like was machining. I really enjoyed machining. Somehow slicing through metals is very satisfying. And so are those things I learned. And of course, I got really, really lucky. I feel really lucky. I got work on many, many research projects. Surprisingly, Ontario colleges has crazy projects lined up for their students. So my first project was a hockey stick testing machine. It's a company who up in the north they make sporting equipment, but somehow they need to prove that their sport equipment coding works very well with different equipments. So they had an idea. They want to make a machine that could swing the hockey sticks and also collecting the data just to prove that their coding, the paint for the equipment is superior. And this project was not done. It was like previously done by other students. And
I didn't record that.
So that's what I got. They say here is what we got so far. The previous students, they made a frame. They used very, very expensive metal. That's most budget went. And you can tell, right? This is a very big machine. It just waves around. It does not accelerate, and it does not stop. And there is a wire behind it. It's about like 2 meters long, and it's very dangerous. It's no safety procedures, and we actually had to stand like 2 meters away from the machine to like see what it does. And there's one more time.
I didn't record that.
Yeah. I mean, we're in Canada, right? We know how hockey works. You're not supposed to circulating your sticks. You have to have a accelerating like swing like this. It does not supposed to go like all the way. And so those are the problems we have to fix because we need some logic. We need some code to make this machine does what we want it to do. And the first thing, we need to switch the motor. The motor they used was a DC motor, which is like a motor we often see in a car. The limit of this motor is we cannot precisely control it. We only can tell you to go forward or backward. We cannot say you stop, like after a certain angle. It just doesn't work that way. And then instead, we used an air cylinder to use the air pressure to speed up the stick. And this design is done by my team member, Susan. Susan used to design cars. So when she got this project, she figured out how we should reconfigure it overnight. I was really impressed. She said she designed way difficult things before. So we also added a little bit bonus, such as a feeding platform. So we were able to use air cylinder to push the platform forward and backwards to receive pucks. So we don't have to be physically there, like feeding a puck with a dangerous machine. So that's another thing we added. So air cylinder is pretty much, we use air pressure to push things forward. It's a really good way to accelerate things. And it does not require too much electricity. And we just need to fill the tank and the machine can run for a very long time. We often see this air cylinder thing actually at the door, like a door holder. If you see your door slowly closing, they're using air cylinder to slow down the motion as well. And then we added another little tinfoil thing. It's called strain gauge. We use this to measure the curvature of the stick when the pressure is applied. So here's the finished product, and here's a video. Yeah. We call it Snapshot 2 because it's the version 2. And it's a little bit long wire still out there, but you can see we use Arduino to control the airflow. And it's a very big air cylinder, extremely powerful, and a lot of air. We wired them to go forward and backwards. The whole coding is done in C with Arduino, and I did the coding. There's a big silver box there. The silver box is converting the power because most wall power is way too strong for Arduino. Arduino can only handle like battery powers, which is up to 8 volts. So I have to do that. And then we use the magnetic sensor at the back to know the position of the stick. So we can stop that. But anyways, I guess I skipped the video. But anyways, it was like, should we still see it? I think I feel like seeing this. Okay, skip to that part. So I'm going to show that Susan and Phil. Phil did the machining for the most part. Yes. So the stick is within control now, and we use air to push it forward really quickly and slowly coming back. And The best feature was the safety procedure. We had a safety control box, so the machine would not just keep going without we telling it to. Another feature, we added a grapher for the strain gauge. We collected all the data, all the testing results, and then the result can prove that the coat with and without the coat and the hockey sticks actually lasted longer or can take more pressure. You can tell it's the filming started in the morning and it ended in the evening. It's usually how long it takes to do any movie production. Yes. So I was really proud of this project. It was my first physical project, the first actual commercialized shipped product for hardware. And I want to build something that's in a larger scale, not just a one-off thing. Because this is still considerably easy because I just have one customer. As long as they're happy, I'm done, right? And I want to take more challenges. So I learned a lot after this project. I started to work on more larger scale projects. So I want to talk about why I think choosing the platform is important. And my second project, it's a wind turbine project. I got this project halfway as well. The school actually spent years doing the research. They finalized the wind turbine, and they say it's good to go, but we need to have the first finalized prototype. And we even installed the prototype on the rooftop, and it's up running. Actually, I was just able to review the video because it was under NDA for the longest time. So these turbines are running like crazy, but it's not much wind, and it's just collecting crazy amount of power. It's very small, the size like my size. It's just spinning vertically without the traditional wind turbine, which takes so much space and very heavy, very expensive. And then at the end of the project, we needed something integrated to the internet. We need to collect the data to actually prove that this turbine is efficient. We can collect how much power through how much time and fill how many batteries. And I picked up a free device from the college. Benefits of being a student, you get lots of sponsorships from lots of institutions or lots of companies. This is a device, it's actually industry standard device. It's called ICP DAS. So the beauty of this is it is very solid. It's already able to handle high voltage and high amperage, so I don't have to do too much protection. This thing cost a fortune. I believe this single device costs about 800 Canadian dollars. And yeah, and they just laying around the college. You just saw, yeah, it's free, let's use it. And that was my plan. So I'm gonna get the turbine working and get the turbine and get the ICP DAS. And they already have a software collecting the data. I get that on my computer and upload to the cloud. Seems like a pretty straightforward plan. And their support guide's amazing. That's my first time getting customer support on an enterprise level, I feel. The guy name was John. John was able to help me on the phone for over 5 hours each time. I was like, wow, he has lots of times. Usually other customer support just want me hang up. He would just keep helping me. Oh, you don't know how to do this? Let me help you. But then we, of course, run into problems. We cannot modify the software because it's enterprise. They have their own version of software. The Excel sheet somehow is in a different format, so I cannot upload that to my server because I need to decode the file. So I called John. I said, hey, John, can you please help me? He's in, I believe he was in California, beautiful place. And John was like, don't worry, Macy. I will contact my headquarters in Taiwan. We will give you a new version next day. Do you know what? Surprisingly, I got the new version next day. And part of being a software developer, we know rushed product usually doesn't work right away. So this same procedure happened 10 more times after that. We just back and forth on this update for about a month. Eventually, I got the data. I was celebrating, it took me a long time just to get a spreadsheet upload to my server. But you know what? It's a free device. John was nice. I'm glad I got it figured out. And then upload the data. It worked. Then the next day, it stopped working. And it got me wondering, like, why things just doesn't work the next day. I think it happens a lot in the hardware industry. Like usually in a software, when we make a software, we can get reset, we can roll back to our older version, it will still work. But with hardware, exact same setup, exact software, exact hardware, somehow the next day just stopped working. I did a lot of research, and that reminded me, I had a course, it was called networking. Then I digged in more. I realized the real cost of having our own server, which is our IP addresses changes every day. It's our home IP addresses doesn't change, but when the provider give us internet access, they change our IP address. So I will allow my server access data from certain IP. It will work for a day, and the next day it will be changed. And am I gonna do this every day? Of course not. So I had to call the provider, say, yeah, please give me a static IP so I can have this thing set up. It actually cost a lot of money to have this thing running every day, to have a static IP. And it's just like pouring money to have an IP address that doesn't change. I learned that from my mistake. Just like first was choosing a free device, which ended up costing me so much time. Also choose to have my own server, which cost a lot of time and money. And that's why we really need to do research before we're starting doing some sort of hardware project, because it is not just costing time, it's also cost money. Once we had a solution, say where we want to go, it's just money, just keep burning. It's not like we can just reset our branch, reset the code, just starting again. It's also a lot of hardware, it's involved, a lot of manpower, and a lot of like, if you actually modified your hardware to work with a certain solution, are you gonna recreate your hardware to work with a new platform? And of course, you're here. Let me do the research for you. Here is a chart from Dyson.com. He listed the most popular cloud services providers out there. The most popular three is pretty obvious. Number one is AWS, Amazon Web Services. They're killing it in this market. And second is by Microsoft. Actually, I'm really surprised, but they're doing really, really well in enterprise field. Last but not least, it's the Google Cloud. And then, of course, there's still about 18% of people, they decided to have their own services. I get it, because you get more control. However, it's more expensive. Some people are willing to pay for the price. And we need to also put into consideration about the coverage. I think from the last talk about accessibility, Canada is a very small populated country. Our customer base is very small here. We have to think about if our product gonna expand, is this service provider gonna support me all the way there? Do I have to reset my infrastructure to work, to make sure my products still work elsewhere? The Amazon Web Services has lots of coverage. It's very mature. I think the best coverage is actually from Microsoft. They even support Africa. And last but not least, of course, Google. Google is kind of a new player in the field, apparently. If you're only working with developed countries such as Canada, America, and European cities, you're fine. But you're thinking of going to emerging market, maybe you need to think twice. And then next one is the language, the coding language we're gonna be using for hardware. The first, there's three categories of languages we're using for hardware. The first one is on the constrained devices. I mean like Arduino chips or Raspberry Pi. It's very common, people using C, C++, and also Java. And the JavaScript is upcoming. There are a lot of notebots are built in JavaScript. However, the whole industry has not been catching up with JavaScript yet. Hobbyists use a lot of JavaScript to do coding for robots. However, the manufacturers, they don't use JavaScript. Then second is the gateway. Gateway, I mean how we connect the network, how we set up the network. And actually Java is still taking control over this. I'm not surprised because a lot of infrastructure, they have not been updated yet. They're still using Java. Then on cloud platforms, It sounds really fancy, but it's just pretty much how we navigate our database, like how you're gonna write an API for your device to receive data or collecting data. The most popular one is still Java. So you can see there is a trend here. Seems like Java is still a very solid language for IoT. So if you are still doing Java, don't worry, like you're still gonna be in demand for a very, very long time. And the board. There are many, many hardware chips out there. There are so many hobby kits out there. Let me help you to choose. The first platform is AWS. They support Raspberry Pi. I think that's very common. And also they have lots of their own chips for different languages. They do have JavaScript support, and they have no support. They have C++ support. Recently, Amazon released a camera device, can help you do machine learning and image recognition. It's called Deep Lens. So if you're interested in machine learning, you just want to get a little bit into hardware, but don't want to build the whole thing by yourself, I think Deep Lens is actually a very good way to go. Then second is Microsoft. They work with many, many providers. Even ICP DAS, which is an industry standard for a lot of manufacturers. A lot of factories actually using ICP DAS. So I think that's where their customers are for like heavy duty machines. And of course, Raspberry Pi is still super, super popular. And last but not least, and Google, they're just working on their chip as well. But the product is more aiming towards machine learning for like computing and stuff. Instead of before, they were more focusing on Arduino-like kind of board. So you can tell clearly Raspberry Pi is the winner in this sector. It's cross-platform, so you can kind of switch your provider whenever you feel like. It is actually enforced by the developers. It's not enforced by the providers. It's just because there's so many developers love Raspberry Pi, and all the companies, they kind of feel pressured to support it. And well, can we start making it now? I think it's a very, very common thing for software developers. We love hackathons. We love to make things overnight and get it shipped, right? We can ship a new software maybe 3 months, right? It's our spirit. Just get it done. Well, there is a slow side of making a hardware product. It takes a long time. If you think you can ship a software within 3 months, you maybe can think about you can ship a hardware product within 3 years. And here is prototype to product. And before we really want to ship or decided to really turn our prototype into production, we really need to think if it's worth it, because just the amount of time and resources it would take. Here is just a simple graph I draw of how a cycle would work. So first, you're going to have a prototype. I would say that's probably take you a week. You can probably get a prototype working with some maker kit. And then you have to send that to production. You're going to find a factory who is going to manufacture your product. And then you're going to send to assembly line. And assembly line is a different creature. They don't do things normal people do. And then you're going to improve your assembly line because, of course, the first time it's not going to work well. And then you're going to get feedback. And again, you're going to do the whole cycle again. And that's easily going to take you 3 years. And at first, I mentioned it's very easy to get a prototype. At a hackathon, you can get an Arduino project working with some hacks, some stitches, some LED light, with some help of 3D printer. You can get your prototype done 3 weeks, 3 days, easily. And the challenge is actually to convert it. Because assembly line, they're still very, very traditional. They don't have 3D printer. They don't use Arduino. They don't even use JavaScript. So if you give them your code, they're more than likely to just have to convert it to some sort of C or C++ language. And then they have to change your design. Unless you make a pure plastic product, if you're making any appliances like a kettle or a microwave or a stove, you probably have to redesign your hardware to fit basic standards. There's so many screws out there. I have to actually go through a list to find exactly the right screw to match the size, maybe gonna match my machine. And we are more than likely going to use existing component instead of creating custom components. Unless we're at the scale of an Apple, building our own screws and having our own assembly line, most likely we have to roll back our aggressive design to become very basic. Interesting story is when we were designing the base for our wind turbine, one of the students, he designed a beautiful base. It was like had different curves, it required so many screws, and then our mentor saw the design. He said, well, you designed a very beautiful base, but I'm just gonna use 1, 2, 3, 4, 5 plates to build a cube. That's just the reality of hardware, because curves takes time, and building something beautiful takes time, and the function of the base is just to keep things stable, and we had to scale down, because if we're gonna spend 3 months to build a beautiful curvy base, and all our money and resources will be wasted into something that's not super important for the product. And then, of course, we're gonna send to the assembly line. Hopefully they understand our graph, and hopefully they're not gonna have any questions. Usually you will make 1,000 of your first product, I would say. I think if it's less than 1,000, it's less likely to find assembly line who is willing to take it, to be honest. And then, why not sending them all? I think I mentioned, because it's very hard to predict products, because we are not just dealing with code or dealing with some compile errors, we're dealing with physics, we're dealing with nature, we're dealing with time, we're dealing with frictions, and there's things just happening. So here is an example of a blade. It's not exactly the same blade we used for the wind turbine, but it's just an idea of a blade. It's made in plastic, it's hollow. We initially got about 100 blades, made it locally in Toronto, but when they came back, they looked like kind of like a squeezed water bottle. They were supposed to be flat and beautiful, curvy, smooth on the surface. Of course, our provider is very, very reliable. They're local. We worked with them before. It must be something else, right? Then we realized it actually has to do with how nature works. When a plastic heat up, because when we were making the mold, there will be air in it. When the blade is slowly cooling down, the air needs to get somewhere. And then because the whole blade was sealed and the air just squishes or pushes the blade, it just doesn't look beautiful. And then eventually we had to redesign our blade to include small holes in the middle of the blade to let the air flow. That's just another example of why the first time we don't produce all of our hardware at once. And then once our assembly line is more mature, we knew what we were gonna do, then we're gonna send it to massive production. Then we're gonna get feedback, and I'm gonna make changes. Well, it's another slow sign of making changes in hardware. We cannot just do an update on our Google Play Store. Even like an update on your Google Play. Not all your customers gonna update their app, right? Just think about hardware. When you have a new version of your hardware, not all your customers can even buy that new hardware. And we cannot have like a git or git reset or git push. It doesn't work that way. So here's the example timeline. So we will find the solution maybe a week, and then we maybe get the communication and everything done for like another week, and then at the end we may gonna get a new device made within 2 months. That's very optimistic, not including the waiting time for different chips, waiting time for different switch, waiting time for different USB cables, and then any change is costly. Think about every time you add a feature to your iPhone app or Android app, it's gonna cost you 10 cents more. The more customers you have, the more money you have to spend on it. That's the brutal part of hardware industry, because anything you change, everything you add, it costs money. And then not to mention the cost of delivery and storage. Luckily, we have different providers dealing with that for us today, but still a lot of companies still building their own infrastructures just to keep inventories. That's a lot of cost. And I worked on a device called IoT, took them about 2 years to update their existing hardware. IonQ is just a heart rate monitor device. All it does is measures your heart rate. Took them 2 years to update the hardware. And then Dyson, James Dyson, took him 5 years, and he made 5,127 failed prototypes to come out with the final version of the vacuum cleaner. And it's still worth it. Are you determined to spend 3 to 5 years on your hobby project and turn it into a profitable product? My mystery turbine project, it was really amazing. It was efficient, it was cheap, it was small, and it was affordable. But it did not make it, right? It took 3 years. Because Elon Musk, do you know what happened? He bought Solar City, and solar got so popular. So my whole category of wind energy was just destroyed. Nobody wants wind turbine. I was like, yes, your wind turbine is great. However, this guy, Elon Musk, he just bought like a solar company and he's famous, and government gives them incentives to get like tax deduction on solar panels. So then nobody buys wind turbine. So you're still gonna be successful. Is your hobby project still going to be successful after 5 years when you finished it? And well, the good news is, we have more accessible, we have more things that's available to us. It's cheaper to make prototypes. It's easier to code, and it's easier to sell. We have Shipwire, which handles the inventory. We have Shopify, Canadian company, help you sell things. Yes, we still can't just make things for fun. It never hurts. I have still so many failed prototypes at home. It's still really fun to create them and see them moving around. But we can still make it for profit, just like Elon Musk, right? He make cars, he make like solar panels, whatever. There are people can turn things into product and turn them also make a huge profit of it. So thank you. Here's my talk, and I hope my story and give you an idea of how this whole hardware industry make you figure it out how, I need to reorganize myself. So hopefully my talk can be helpful to you. You can understand what it really takes to have a physical product, why it is so difficult, and what kind of things we need to think about before we decide to move forward. Because it's gonna be a long journey, and you have to be very, very determined to ship it. So thank you.